Yeah. So friends, today we will discuss floating point representation. Yesterday in one of the section I have discussed the theoretical part. We did not really see it practically, but in one section to certain extent we have done. So since it's an important topic, let us revisit this particular topic again, right? So I'll be sharing my screen. I have already shared my screen. This is the board where I am writing. So the topic name is IEEE 754 notation. So IEEE 754 is a standard. IEEE 754 is a standard for representing floating point numbers. Okay. So IEEE 754 standard for floating point numbers. So friends, floating point numbers, the way floating point numbers are stored is totally different. Yeah, the way IEEE 754 standard defines the representation of floating point number is totally different. So the as a programmer, what we will do is we will write something like this: float x is equal to some 13.25. But exactly how a floating point number is stored inside the computer, that is what we need to understand. And it is based on a standard called as IEEE 754 standard. So friends, the difficulty in storing a floating point number is how do we store a point? So 13.25, storing 1325 is not a problem. Storing 1325 is not a problem. But in floating point number, the position of the point is not fixed because 13.25 is a floating point number, 1.325 is a floating point number, 132.567 is a floating point number. So the problem with floating point numbers is the position of the point is not fixed, and hence where do I store the position, or how do I store the position of the point? At the max, I can store a point using any one binary bit called as 1 or 0. So I can store a point, but how do I store the position of the point? Because it is not fixed. In a given number, it can be after 2 digits, it can be after 3 digits, it can be after first digit. So it is highly difficult to store the position of the point, and hence storing floating point numbers is challenging, right? So let us try to understand how floating point numbers are stored as per IEEE 754 standard. So as per IEEE 754 standard, floating point numbers are stored using M into R power E format. M into R power E format, where M is mantissa, R is radix, and E is exponent. Right? So friends, there are certain important points which we need to understand before we move on to representing a floating point number using M into R power E. There are certain important points. Point number one, we don't store a dot. Right? We are not storing 13.25. That point we are not going to store. It's not possible. Second point, the format used is M into R power E, where R is always 2. You know very well, R is always 2. R means radix base. Base will be always 2. Why base will be always 2? Because the number system we are dealing with is binary. So since I know R is always 2, I need not store it explicitly, right? It is assumed, it is by default. Now, third important point, this so-called mantissa is there, right? We apply something called as normalization on our floating point number. So normalization of the number is compulsory. Okay. What do you mean by normalization? What do you mean by normalization? Normalization means, for example, 0.25 is there. It is one floating point number. 1.36 or 30 is there. It is a floating point number. 2.42 is there. It is a floating point number. Process of normalization is, normalization says you have to convert every floating point number into a format which will look like this, 1 point something. Right? This format is called as normalization. For example, 0.25 is there. How do I represent 0.25 in 1.xxx format? So I'll multiply 0.25 into 2. I'll get 0.5. Then 0.5 into 2. I'll get 1.0. Like that, you have to make sure the number is normalized. Okay. You will understand normalization when we solve one example. So what do you mean by normalization? Normalization means every number should look in this form, 1 point something. It should not be 2.4 or 0 point, nothing is allowed. Normalized number will look like this. So in these three numbers, this is normalized. Okay. So point number 4 is exponents are always stored as positive number using bias. So exponents are always stored as positive numbers using bias. Please don't misunderstand my statement. I am not saying exponent cannot be negative. Exponent can be negative. Exponent can be negative like this. 2 power minus 3. It is possible. 2 power 3 is possible. 2 power 7 is possible. 2 power minus 9 is possible. I am not saying exponents can't be negative. What I am saying is inside the computer uses only positive representation of exponent, because handling both negative and positive exponents is difficult. So internally exponents are represented as only positive numbers. Then you may ask, sir, how is it possible? Minus 3 is my exponent. How you will store it as a positive number? For that, we use a concept of bias. Again, when we discuss our example, you will understand what is bias and how bias is useful. So before we move on and solve one example, I want to know, or I want to understand from you that up to this point, right, the IEEE standard M into R power E and these 4 points are clear to everyone or not? Please respond in the chat box. Very few students have joined the class, right? These kind of things will be monitored. These kind of things will be observed, right? So whenever there is an online class, Anyhow, it's a holiday for you. So at least you should have attended the online class, right? So please inform your friends at least down the line next time it should not happen. So what is the response in the chat box, right? So any doubts till this point? Yeah, why R is always 2? R means what? Base of a number system. R is base. Now, what we are trying to do, we are trying to convert a decimal number, floating point number, into binary form. So since I am dealing with binary number system, I want to store floating point number in binary form, right? So since my destination number system is binary number system, so obviously what is the base? Base will be 2. And always I will convert any given decimal number into binary only. That's the reason I am saying R is always 2, right? And by default it is 2 because I am dealing with binary numbers, and hence I am not going to store it separately. It is assumed R is by default 2. So is it clear, Nitya? Done. So let us move on. We will take one example. Let me solve this example. After that, we will discuss another example, right? It should be very, it should be completely clear to everyone. If you have any doubts, please don't hesitate to ask. Let me solve one example. Hmm. Okay. I think 13.25 base 10. So the same example we have actually used in yesterday's class in one section. So we have converted 13.25 into binary, right? So I'll explain the same process again, right? Same example we will take, but in some other section we did not discuss the example. For AIML students, it will be like a repetition, right? But this is a very important point. So friends, before I convert this 13.25 into uh, binary number, right? First of all, I should know what type of hardware I am using, right? So hardware means what is my CPU? Is it a 32-bit CPU or 64-bit CPU? So it depends on the CPU. So when you are using your programming, what we say, languages, at that time, you are not worried about all these things, right? Maybe in your PPS faculty might have told you like integer, you get 2 bytes in some hardware and you get 4 bytes in some hardware, especially you get 2 bytes in a 32-bit machine and 4 bytes in a 64-bit machine. Similarly, if I get 32-bit, right, then how floating point number will be converted into binary form? If my machine is a 64-bit, how floating point number will be converted into binary form? So before I convert a floating point number into binary, I need to know the type of architecture I am using. Is it a 32-bit machine or 64-bit machine? So friends, actually converting a decimal number into binary is simple, which we have done in our earlier classes in the probably second or third class of our subject, decimal to binary conversion. But today what we are trying to understand is, okay, decimal to binary conversion we have done, but how these floating point numbers are actually stored inside the computer, right? So the hardware level issue we are trying to understand. So let me assume, so first I need to confirm what is my machine. So friends, let me assume mine is a 32-bit processor. So what is my processor? It's a 32-bit processor. Fine. It's a 32-bit processor. Now, if the processor is 32-bit, then 32 bits are given to store the floating point data, right? Out of which 1 bit will be for sign, means positive number or negative number. So positive means 0, negative means 1. So 1 bit will be for sign. 8 bits will be allotted for mantissa. I'm sorry. 8 bits are given for exponent. How many are left? Out of 32, 1 bit for sign, 8 for exponent. So 1 plus 8, it is 9. I am left with another 23 bits. 23 bits are allotted for mantissa. Right? Now, how exactly this is done? Let us try to understand. Let us start with the conversion first. So friends, you know very well 13.25. What is the binary code of 13? What is the binary code of 13? Apply 8421 code. 8 plus 4, 12. This is 0 plus 1. So binary code of 13 is 1101. Right? Now, this 0.25 is there. What is the binary code of 0.25? So how do I convert it? How do I convert it? 0.25 into 2 is 0.5. Now you have to take only this part, and what is this part? 0.5 into 2. This kind of multiplication you have to repeat till you get 1 as the answer. So luckily in this case I got 1 in the second step. So friends, please observe, I have not taken this entire part in the second step. I have taken only the right side part. Unfortunately, both are same in this example. For example, if this is, let us say 1.5, let us assume, then I will take this 0.5 and I'll use it here. So it is not 1.5 which I am taking. So what I am trying to say is, I am taking this right side portion as input to the second step, not the entire answer of first step. So I hope it is clear to you. So 0.5 into 2, 1.0. This multiplication process you have to repeat till you get 1.0. I got 1.0 in only 2 steps. I'm lucky. Now collect these bits from top to bottom. Which bit? The bits which are there before the point. So what is the answer? 0, 1. So 0, 1 is the answer. What is the binary code of 13? Binary code of 13 is 1101. Point. What is the binary form of 0.25? It is 0, 1. So this is how I'll convert a decimal number into binary. 1101 into 01. 1101.01 is the binary form of 13.25. Let me confirm whether this is correct or not. How do I confirm whether it is correct or not? This is the binary number. Convert this binary to decimal. What I should get? I should get 13.25. Let me check that. 1101.01. Multiplication method is done, applied when we convert binary to decimal. Division is done when we convert decimal to binary. So I should do multiplication. And you know very well how to do multiplication. First bit, it is 1 into 2 power 0 plus 0 into 2 power 1 plus 1 into 2 power 2 plus 1 into 2 power 3. So from left to right, if I am moving, the exponent will increase. But friends, in the fraction part, the exponent will decrease. 0 into 2 power minus 1 plus 1 into 2 power minus 2. In this direction, exponent will decrease. Now, what is 1 into 2 power 3? 8. 1 into 2 power 4, no, 2 power 2 is 4. 0 into anything is 0. 1 into 2 power 0. 2 power 0 is 1. 1 into 1, it is 1. Point. What is 0 into anything? It is 0. Plus 1 into 2 power minus 2. 2 power minus 2 means what? 1 divided by 2 power 2. So when I add all these things, it is 13 point. This 0 is anyhow gone. It is 1 into 1 by 4. 1 by 4 means what? 1 by 4 means 0.25. So 13.25. So I got my decimal number back properly, right? So binary to decimal I have done. I have confirmed that my decimal to binary conversion is correct. So what I have done, 13 was converted into binary using 8421 method. Fraction part was converted using multiplication and collecting the answers from top to bottom. That process we have done. We got the binary form of 13.25. IEEE 754 standard is not yet applied. Only conversion we have done. Now we have to see how this floating point number is stored inside the computer. Now, before I explain this IEEE 754 standard, confirm me, tell me whether this decimal to binary conversion, which involved fractional numbers, is it clear to you or not? Please confirm in the chat box. So there are no doubts for anyone. Almost everyone says it's clear. Nice. Right. So let's move on. So 1101.01 base 2. This is my floating point number. So I'll be applying my IEEE 754 standard now. I'll be applying my IEEE 754 standard now. So point number 1, tell me, is it a normalized number? Is it a normalized number? What do you mean by normalization? Normalization means 1 point x, x, x. I want the number in this format. So where is the dot? Dot is somewhere after 4 digits. I want the dot to come here. I want the dot to come here. So what I will do, I'll write like this: 1.10101. I have moved the dot from its current position to left side 3 times. So obviously the value of the number will change. If you look at this one, it is like 1101.1 paisa. But if I move dot here, it becomes 1 rupee, one rupee, then followed by some paisa. So if I simply change the position of the dot, the value of that number is changing. Value should not change. So what I will do, I'll write like this: into 2 power. Tell me what is the exponent. When I move the dot 3 times to the left, then how do I write the number? 1.10101 into 2 power. Tell me, what should I write? 2 power. Yeah, there is no confusion, right? It is not minus 3. It is 2 power 3 because already I am moving in the left direction, right? So the magnitude of the number has actually decreased, and in order to preserve my value, right, I'll be using the exponent 2 power. How many times the dot was moved? 3 times. 2 power 3. If the dot has moved towards the right side, then it will become 2 power minus some other negative exponent I'll get. So step 1, Is it normalized or not? Yes, normalization is done. The number is normalized. So why we are doing normalization? The idea of normalization is any given floating point number, if it is converted into this part, this format 1.xxx, if it is made a uniform standard, if it is made compulsory that every floating point number should look like 1.xxx, then what is the advantage? For every number, I know that this one will be fixed on the left hand side. Yes or no? Since the number is normalized, since it is 1 point something, I always know that before the dot it is 1. And hence I need not store this. Means I need not store separately for every number. For every floating point number, I will assume that before the dot there is a 1 and I'll substitute that 1 every time. So separately, I need not store this 1. Okay, this is assumed now. This is assumed. Now what I am left with? I am left with this fraction part. What is the fraction part? 10101 into 2 power 3. Okay. Now I need to apply my m into r power e. I know radix is 2, exponent is 3. So friends, in a 32-bit machine, how many bits we are getting for exponent? 8 bits we are getting for exponent. With 8 bits, how many different numbers can be represented? With 8 bits, 2 power 8 different numbers means 256 different numbers can be represented. If I divide 256 into 2 halves, why I want to divide 256 into 2 halves? Because exponent can be positive, exponent can be negative. So to divide these exponents equally between positive and negative exponents, 256 by 2 I will do, which is 128. So what are the possible exponents? Minus 128 to plus 127. Because there is a 0 in the middle, I end up at 127, not at 128. So friends, these are the possible exponents allowed in a 32-bit machine. Minus 128 to plus 127 is the possible exponent that is allowed in a 32-bit machine. Now, in the 4 points which we have written, we have clearly mentioned to avoid confusion or handling both negative and positive numbers, exponents are actually stored as positive numbers using bias. So what we will do is, what is the largest possible exponent plus 127? So what we will do is, we will use 127 as bias. So what do you mean by this? If the exponent is 3, what I will do is I will store 3 plus 127, right? Or you can say 127 plus 3, both are same. I'll store 130. If the exponent is 3, I will store 130. Suppose if the exponent is minus 3, then I will write like this, 127 minus 3, it is 124. So the idea is, if there are negative exponents, still I want to store a positive number. So what will happen? What will happen? Any negative exponent which is there, like minus 3, minus 27, the negative exponent will be subtracted from 127. That difference is stored. If the exponent is 124, what do you mean by that? It is minus 3. Suppose if my exponent is minus 27. So what I will do? I will subtract 27 from 127. I'll get 100. So I'll store 100. So if you find 100, means a number which is less than 127 is a negative exponent. Any number which is above 127 is a positive exponent. If the exponent itself is 127, then it is 2 power 0. So please tell me, is it clear? What do you mean by exponent part? Is it clear? Please respond in the chat box. Is it clear? Exponent, why we are using bias and how we are representing both negative and positive numbers. Is it clear? Respond in the chat box. Fine, that's great. Very few people are responding. Done. Okay, we'll move on. Thank you. So what is the fraction part? 10101, right? So 10101 into 2 power 3. This is what is our floating point representation of the number. 1 point actually, that one we are assuming, right? Inside a computer, that one is not separately stored every time. It is always assumed. Whatever mantissa is there, I will assume that it is 1 point so and so mantissa. So that 1.1 is already assumed. So this is my mantissa. This is my radix. Now what should be the exponent? Exponent should be like this. 10101 is mantissa. This is radix. Exponent is 127 plus 3. So it is 10101 into 2 power 130. Now friends, this is mantissa. This is radix. This is exponent. Radix is also not stored every time because I always know that radix is 2. It is assumed. So I need not store it. That's the reason in IEEE 754 standard, 32 bits are distributed for what? 1 bit for sign, 8 bits for exponent, 23 bits for mantissa. And also remember the order, sir. This is the order. You need to follow the order also. Now, 13.25, when we started our discussion, 13.25, was it a positive number or negative number? It's a positive number. So, positive is 0, right? So, I'll write a 0 to represent the sign bit. After sign bit, I should use 8 bits to write the exponent. What is the exponent? 130. So what is the binary code for 130? What is the binary code for 130? Apply 8421 code. 8421 16 32 64 128. So it is 128 plus 2, right? So 1 0 0 0 0 0 0. 1 followed by 5 zeros followed by 1 0. Total it's a 8-bit number if you observe. So that 8-bit exponent I am writing, sir. 1 0 0 0 0. I think 5 zeros, right? 1 2 3. Yeah, 5 zeros 1 0. So friends, this is the exponent. How many bits are there for mantissa? 23 bits. Now please observe what is the mantissa I have. I have 10101 as the mantissa. And this mantissa is nothing but the value which is after the dot. After the dot. Now tell me, I should make this as a 23-bit number. But how many bits are there present in the mantissa right now? Only 5 bits. Another 18 bits I should add, means 18 zeros I should add. That is called as padding, Padding. Now tell me, shall I write 18 zeros at the end of this mantissa, means on the right side? Shall I write 18 zeros here like this? Or shall I write 18 zeros first followed by 10101? Right? Let me know. Where should I add 18 zeros after the mantissa? Before mantissa or after? Because I need to make this a 23-bit number. So 10101 is there. I need to make it a 23-bit number. 18 zeros need to be written. Shall I write before 10101 or after 10101? Before. Why 8 bits are given? I'll let you know. After Mantissa, right side of Mantissa. Some people are saying before. So friends, please observe here. We are our Mantissa is something which comes after dot, right? 13.25. We are talking about this part. 13 is we don't have an issue with this one, right? 1 point something. We converted this into 1 point something, right? And this one is already stored, assumed. We are dealing with this part. We are dealing with something which is there after the dot. Now, what will happen if 10101 is like this? What are the exponents? What are the weights of these position? This is 2 power minus 1, 2 power minus 2. This is 2 power minus 3, minus 4, minus 5. If I add 18 zeros here, it will become 2 power minus 6, minus 7, minus 8. Like that, it will continue up to 2 power minus 23. If I write 18 zeros after 10101 means if I pad 18 zeros in the right side, it will not change the value of 10101. Suppose if I put 18 zeros before only, 1, 2, 3, 4. Imagine these are 18 zeros. Now I'll write 10101. Then what is the exponent of this one? It is 2 power minus 19. This is 2 power minus 20. This is 2 power minus 21. 2 power minus 22. And this is 2 power minus 23. Actually, what are the values? These are 2 power minus 1, minus 2, minus 3, minus 4. These are first 5 digits after a dot, whose exponents are 2 power minus 1, minus 2, minus 3, minus 4, minus 5. If I put zeros before, then I am changing the value. 2 power minus 1 is becoming 2 power minus 19. I hope you understood why zeros should not be added before, it should be added at the end, because we are on the right side of the dot. So to make sure that the value of that number does not change, zeros need to be added only on the right side. Is it clear? Someone told it should be before, right? Is it clear, sir? The one who wrote before, no? For him I am asking, is it clear why it should be written at the end? Yeah, thank you. So, where is my 8? Now I am trying to write the 32-bit answer. 1 bit for sign. 8 bits is my exponent. 130 is binary code. 1 followed by 5 zeros followed by 1 0. So friends, this is sign bit. This is 8-bit exponent. And what is my mantissa? My mantissa is 101015 5-bit, but 23 bits are allotted for mantissa. So 1, 2, 3, 4, 5, 6, 7, 8, like that. 23 zeros I will write. Total it is a 32-bit code. So internally, right, internally our floating point number 13.25 was actually written as 1101.01. Then we made it 1 point something. And finally, the floating point number gets stored in this form, right? Now coming to the question, someone was asking, sir, why it is 8-bit only, right? So to represent the sign of a number, 1 bit is enough. So I am done with 1 bit. Now, this is the architectural issue. Why I am giving 8-bit exponent? What is the biggest possible exponent I can give for 8-bit? Positive not one, because 8 bits means positive and negative bits are there. So I will divide with 8, I'll get 256 combinations, which are divided into 2 halves, minus 128 to plus 127. So what is the biggest possible exponent I'll get? 2 power 127. So in a 32-bit machine, there is a limit for the biggest possible number which can be stored, and there's a limit for the smallest possible number which can be stored. So beyond that, it cannot store. And that's the reason the exponent is decided based on the underlying hardware. And whatever is balanced, that is for my mantissa. Suppose if I am using a 64-bit machine, if I am using a 64-bit machine, in a 60, of course, all are 64-bit machines now. Even if it is a 64-bit machine, sign bit is only one, because positive or negative to tell that I need one sign bit. Now here we are getting 52-bit for mantissa. So how much is left? 52 plus 1, 53. 64 minus 53. This is 1. This is 1. 11 bit for exponent. Right? Some people will think that 8 is the number of bits per exponent in 32-bit machine. So by default, it will be 16 in a 64-bit machine. No, it's not like that. It is only 11 bit. Again, I'm telling you why it is 11 means again 2 power 11. I think you will get somewhere around 1022 like that. It will be divided into two halves, and based on the biggest possible number which can be stored in that machine, accordingly the exponent will be decided, right? So 13.25, finally how it got stored, how a floating point number got stored inside the computer, that is what we have discussed today. Please let me know, is it clear to everyone? There are a few more points to be discussed, but before that, let me take confirmation from you that converting floating point number to binary is simple. But knowing how that binary number gets stored inside the computer is a different thing, which depends on IEEE 754 standard. I hope it is clear. If not, please let me know in the chat box. I just wanted to know from you whether the process is clear or not. Always sign exponent mantissa format or decimal numbers represented like how m into r power format is used exactly. Manish, I did not understand your question. Always sign exponent mantissa format or decimal numbers. No, sign, of course, it's a decimal number, but it has to be stored in the form of exponent. See, everything is a decimal number when we are using it. Our number system is always decimal, but internally when it's get converted, like exponent is 8-bit, we said. What exponent we got in this example? 130. So for us, it is 130, which is a decimal number. But internally, how it was stored? It was stored as 1 followed by 5 zeros, then 1 0. It's binary form, right? Same is the case with mantissa. Is it clear, Manish? Any other doubts? Y8, yeah, it's a 32-bit machine. In 64, it is 11 bits. I like in the final answer of decimal number, I had this doubt. Again, it's not clear. Final answer of decimal number means our input was this one, right? We started with this question 13.25. When I convert 13.25 into binary, this is what I got. This is the binary form of 13.25. Decimal to binary conversion, we know very well and we have done it. Now, how this particular binary number is stored inside the computer. So this should be converted into 1 point something like this. This one is assumed, this part is assumed, and I need not separately store it. Now I am left with this part. On this right hand side part, after dot whatever is there, 1 point followed by something. On this part, we are applying our IEEE 754 standard. Right? This is what we have done. This is what we have done in this example also. Right? Is it fine, Manish? Yeah, fine. Any other doubt, sir? Any other doubt? Can anybody answer me a question? What do you mean by single precision and what do you mean by double precision? What do you mean by single precision? What do you mean by double precision? Can anyone answer this? I'll be happy even if you see in internet, I don't have problem. Hmm. Yeah. Decimal accuracy up to 1 point. Okay. After 1 point, after point one value. Okay. Anything else? Any other answer? Right. Okay. Hope you understood why the data type in C, why the data type in C was named as float. We have used float data type, right? We have used float data type, single precision, double precision. Okay. Ramcharan, do you mean that only 3.1 point Google is telling it? Fine. It's okay. That's great. Chalo. So, so to summarize, we were discussing floating point numbers, right? Floating point numbers. Why they are called floating point numbers? Because these are all floating point numbers, right? 12.3, 123.45, 1, 2, 3, 4, 5.67. So in all these numbers, if you observe, the position of the point is not fixed. It is after 1 digit, after 2 digits, after 3 digits, after 4 digits. So these are the numbers, right? Fractional numbers, real numbers, in which the position of the point is not fixed. So I say position of the point is floating. And hence these numbers are called as floating point numbers. So based on this concept only in C programming, we have a data type called as float. Based on this concept, we have a data type called as float. Now, float will only permit you single precision. Means there is a limit on how many digits that you can represent after a dot. The moment I say this is not sufficient, I want to go for a double precision. That's the reason you have a data type called as double. So friends, the names of the data types are also based on the underlying representation of floating point numbers. Right down the line, somewhere in future, people may ask you why double is called as double, why float is called as float. So people are trying to check or validate your fundamentals, right? That's the reason I said, CO is the oldest subject and most important paper. So I can ask a lot of questions in programming which are related to computer organization. So do you know float data type? You say, yes, I know float data type. Do you know why it is called as float? So people are trying to check, do you know what exactly happens when a floating point number is stored? Now, hope these two things are clear. Now, another important point. I told you in both the classes, floating point arithmetic, floating point arithmetic operations generally don't give you exact answers, accurate answers. Floating point arithmetic may not give exact answer every time. Exact answers every time. So what is the reason? What is the reason? Especially in C language, you might have noticed if at all you have dealt with very large floating point number or very small floating point number. I'll give you an example. 10 by 3, what we will get? 3.33333. It will continue like this, right? Now suppose if I am trying to convert this into binary form, where do I stop? Where do I stop? How long I should do this process? So can you guess what should I do if I am trying to divide 10? If my value is 10 by 3, if my value is 10 by 3, what is the answer? Is it 3.3 or is it 3.33333? How many threes? Right. Suppose if you are solving this using pen and paper, then I can tell you, come on, write how many possible threes you can write. You please continue writing. Maybe you can write 100, 200, 300 or 3000 times. But inside a computer, how this is managed. So why we don't get accurate answers in floating point arithmetic means if there are many such numbers, right? Where we don't end up with the division process. So 10 by 3 is one example where we say 3.3333333. How long it will continue? So if I am using a 32-bit machine, I have space for 23-bit mantissa. So I will continue the division process, means the processor will continue the division process up to 23-bit mantissa. It will run this up to, means whatever is the capacity, I can hold a 23-bit mantissa, right? So 23-bit mantissa, that much, to that extent division will be done and that value will be stored. Now same division or floating point arithmetic, if I am doing in a 64-bit machine, it can accommodate up to 52 bits of mantissa. Then it will end up storing a 52-bit mantissa. Means the number which was stored 10 by 3 was stored differently in a 32-bit machine and 10 by 3 was stored differently in a 64-bit machine. But of course, both are not correct because we can't end this division process. That's the reason you may not get accurate answers, right? And you can even see different answers for the same floating point arithmetic depending upon the processor which you are using. So if I use a 32-bit machine, I may get a different answer. If I use a 64-bit machine, I may get a different answer. That is what happens with floating point numbers. And representing very small floating point numbers is also difficult when we say 0.0000789, something like that. But there are many real-time applications in which floating point arithmetic plays a very important role. And there we don't have any luxury to entertain the errors. For example, stock market applications are there, weather forecasting applications are there, oil and natural gas exploration is there, right? There are many seismic applications, many real-time applications in which we deal with very large floating point numbers and very small floating point numbers where I am not going to tolerate any kind of difference, any kind of minute difference in the answer. I am not going to tolerate. It is going to create a lot of problem to me. So in such applications, it is recommended not to use programming languages like C. Then obviously you may ask, do you have a solution? Even in Java, if you use primitive data type like float and double, the same problem can occur. But in Java, we have a class called as big decimal. in which this particular problem is beautifully addressed. And of course, in Java, anyhow, you're studying Java in this semester, definitely you will come across big decimal class, and the same thing will be discussed by Java professor. You will definitely come across big decimal class. So hope the way floating point numbers are represented using IEEE 754 format, is it clear to everyone? Is the conversion clear to everyone? Kindly respond in the chat box. That's great. Fine. So we'll take a break of half an hour, and 11:30 in the same link, DBMS faculty will join, and there will be a DBMS session today at 11:30. So you can probably rejoin at 11:30. Thank you, everyone. Thank you for attending.